radio waves and noise in communication systems. Communication systems involve not only resistors and amplifiers and transmission nodes, it also involves a cascaded connection of networks or circuits or amplifiers. If we have amplifier 1 with noise figure 1, amplifier 2 with noise figure 2, and so on until we reach amplifier N with noise figure N, connected in cascade, and there is a resistor here generating the noise. And assuming that the system is matched here, assuming that it is matched, as you can see here, and assuming that the temperature is equal to T naught. Now the signal output here, PSO over PSI, the signal here, is equal to the total gain A1 times A2 times A3 up to N. So it is product of I from 1 to N. This means this is equal to this is equal to A1 times A2 times A3. This is equal A1 times A2 times A3, etc., etc., until we reach AN. Application of the individual gains to the total gain. Now, because in the noise figure we will need PSO over PSI, and also will need PNO over PNI. Now PNI, the input noise is coming from here. It is KT naught delta F for matched case. Noise output is equal this noise here multiplied by all the gains. So it is multiplied by this capital A, by the product of the gains. This is the input noise multiplied by the product of the gains. It will give us the output noise due to the resistor only. Now the amplifier here also, it adds its noise, its own noise. The noise here is equal F1 minus 1 times KT delta F. This is at the input. At the output we multiply by A1. This is the noise here, and we multiply, and this noise is amplified by A2 by A3 until AN. So we will multiply by A2 A3 until AN, until we reach the last stage here. The noise here is equal Fn minus 1 times KT delta F at the input times AN to find the noise at the output. So this is the summation. Now if we take KT naught delta F common factor, we will end up with this here, product of A, here F minus 1, A1 times A2, etc. It will give us, this is the product of A, this is A, this is capital A, the product until we reach this here, and we will have Fn minus 1 times AN here. Okay, now we put these expressions in the noise figure expression. PSI over PSO, PSO over PSI is 1 over A. The signal output or signal input is equal A1, A2, A3, etc. until we reach AN. Now PNO over PNI, this is PNI, we take, this is PNI from the resistor. So PNO over PNI is equal to this expression. This is PNO over PNI. We take this expression to here. Summation of AI plus f minus 1 summation of ai from 1 to n from 1 plus the last one is fn minus 1 times an. If we divide by a, this is a. In fact, this is a. So a by a is 1. And this is f minus 1, and this is a also. A by a is 1. Plus the last one, fn minus 1, an over a. So we'll have a1, a2, a3 until an. We delete an. We will have a1, a2, a3 until fn minus 1. Until n minus 1. So the final result is this: f equal f1 plus f2 minus 1 over a1, f1 over a1 plus f3 minus 1 over a1 times a2 plus f4 minus 1 times a1, a2, a3. We keep multiplying a until we reach the number before this ending, just before this. If this is n, fn minus 1 to the fn, not to n itself, of course, here. Fn minus 1 is equal to, you multiply a1, a2 until you reach the number before n, which is n minus 1. So this is now communication systems involve also transmission lines. We want to see or to find the equivalent noise temperature and the noise power of the transmission line, both at its input and at its output. I will not go through this detailed derivation because it's not relevant to the contents of this course. This is pure EM. I will jump into the result, which is quite simple and convenient to absorb and understand. This is the result that we want. Okay. This is the result. The noise power at the output of the transmission line is equal kT delta F, we are familiar now with this term, times L minus 1 divided by L. It is the same result as that of the amplifier, but we use here F instead, L instead of F, and 1 over L is the gain. The gain is 1 over L because transmission line has attenuation. So 1 over L is the gain, which is attenuation in fact. If we want the noise power at the input of the transmission line, we will remove L. It will be kT delta F times L minus 1. And we already have derived this, no need to derive it again. Now communication systems has an important element, which is antenna. Usually every communication system has an antenna or antennas to operate, to radiate. That's why we are studying here radio wave propagation. The equivalent noise temperature of the antenna is not the actual temperature, the ambient temperature. No, it is the equivalent temperature of the noise, the system temperature, as equivalent noise system temperature, as we explained before. In the high frequency band and below 30 megahertz, the noise equivalent noise temperature of the antenna reaches or ranges between 100 Kelvin to 10 to 15 Kelvin. Well, this is very, very huge number. 10 to 15 Kelvin. Okay. 10 to 15 Kelvin. This is equivalent noise temperature, which indicates that the noise is very high. At higher frequencies, for frequencies between 50 and 500 megahertz, the atmospheric noise becomes negligible and the cosmic noise becomes, or galactic noise becomes higher. Above 1 gigahertz for the microwave frequencies, in fact it is above, the cosmic noise becomes negligible and there remains the contribution of oxygen absorption in the atmosphere. Now, how to calculate the noise temperature of an antenna. We use this equation. T antenna equals summation of alpha k tk. K is an index from 1 to n. Alpha is the fraction of the total radiation from the antenna when it is transmitting, which is absorbed by a region, and Tk is the temperature of that region. If we have an antenna here, if we have an antenna here and it is radiating, okay, this is the radiation pattern. Now if the main beam, for example, is radiating towards a certain body here, for example the sky, with a certain temperature here of Tk, here Tk, and these side loops are radiating towards the earth, for example, this is the earth with another temperature. This is Te, for example, and if those are for example radiating towards another, assuming that it is another object with a different temperature of T, for example S, TL, for example, then this formula means that we know the total power radiated from the antenna, or now the portion of the percentage of the power in this direction divided by the total power, this is alpha k, and we multiply this by Tk, and the portion of the power radiated towards the earth is divided by the power radiated towards the earth divided by the total power is the portion of the radiation towards the earth, and we multiply it by Te, and we add these two values. Then we add also alpha L times TL. Alpha L is the portion of the power radiated towards this region times the temperature of this region. Let's take an example to understand the idea. Consider an antenna beamed upward at a satellite-borne transmitter, and suppose that the main beam and first side loops, which contain 90% of the radiated power, see an average temperature of 20 Kelvin due to oxygen absorption. The other 10% of the side loop and back radiated power sees a warm earth of 300 Kelvin, which reflects skyward. Say 50% of the incident power. Then let me draw to explain here. Here this is the antenna. The earth, it is radiating towards a satellite with the main back loop and side loops. Now here 90% of the power, 0.9% of the power, 9% is radiating towards the sky, which has an equivalent temperature of 20 Kelvin here, 20 degrees Kelvin. Okay. And this side loop is radiating towards the earth. It is radiating 10% of the power. The side loop and the back loop. Now the earth absorbs 5%, and 5% is reflected towards the sky. The earth has temperature of 300 degrees Kelvin. How can we calculate the antenna noise temperature? We multiply this portion is 90%, so multiply 0.9 times 20. 0.9 times 20. And this 5%, 10% is divided between 5% and 5%. Here also 5%. 5% has a temperature of 300, because this is 0.5 times 0.1 is 5%. And the other 5% has 20 degrees. 0.5 times 0.1 is 0.05, which is 5%. The total is 0.9 times 20 is 18, plus 0.05 times 300. 0.05 times 300 plus 0.05 times 20. The answer is 34, as you can see it is here, 34 Kelvin, 34 degrees Kelvin. That's how we calculate the noise temperature of the antenna. The noise temperature of the antenna is related to radiation resistance as well as conduction loss resistance. So V squared, the total power squared, voltage squared, is equal V R radiation squared plus V conduction loss squared. Now V noise squared, we remember it was 4 R A T, that this is the thermal noise squared. Delta F will be the same for the three quantities, and K is the same constant, 4 is the same, so we're left with R times T, so multiply T for the antenna times R, the total resistance, is equal T antenna, because antenna temperature is related to the radiation resistance, plus T naught, the conduction resistance has the ambient temperature, T naught times RC. If we divide by R, we will get this R over R and RC over R. Now by definition, the radiation resistance over the total resistance is the radiation efficiency. Eta is the radiation efficiency. And RC is equal to total minus R radiation. Total R over total R is 1, and R radiation over R is eta. So this is 1 over 1 minus eta. So T antenna is related to the efficiency of the antenna, and T naught, the temperature of the conduction loss, is related to the remaining part of the efficiency, 1 minus eta losses, as you can see. Here, if the antenna is connected to a transmission line, we simply add the equivalent noise temperature of the antenna and the equivalent noise temperature of the transmission line as the input, because we said it was L minus 1 T, minus 1 times T. L is the loss of the transmission line. Let me consider this example here. This is a transmitter. P input here is, we are requested to find the input power. Transmitting antenna. The gain of the transmitting antenna is 40 dB. The distance between transmitter and receiver is 30 kilometers. The gain of the receiving antenna is 40 dB. And the loss of the transmission line connecting the receiving antenna and the mixer is 10 dB. The mixer here has conversion loss of 6 dB and has noise figure of 10 dB. And the intermediate frequency amplifier, IF amplifier, has bandwidth of 10 megahertz and noise figure of 4 dB. The signal, we want the signal to noise ratio at the output of the receiver to be 30 dB. This is called here the super heterodyne receiver. The operating frequency is 6 gigahertz and the wavelength is lambda naught E over F light 3 times 10 to 8 divided by the frequency 6 gigahertz. 6 times 10 to 9 giga is 10 to 9. Here. This is 3 over this is 0.5 divided by 10 point 0.05 0.05 meter. 0.05 meter is 5 centimeter, as we can see. The antenna temperature is 100 Kelvin. There is a solution here. There is a better solution. It's a simpler and better solution. Another solution for the same problem here. So we have the here the transmitter. The gain is 40 dB. We said distance is 30 kilometers, and the transmission line is 10 dB. The conversion loss of the mixer is 6 dB, and the noise figure is 10 dB. For the IF amplifier, delta F is equal 10 megahertz, and F is equal to 4 dB, and the required signal to noise ratio is 30 dB. So we want to find the input power to obtain this. The wavelength we said is 5 centimeter, and T antenna is 100 Kelvin. Okay, now this is the solution, simpler and better solution. Here you can see the system temperature directly. We take the antenna as a reference. This is the antenna temperature TA as the receiving antenna. Here, take here. Our reference is here. The antenna is here. Plus the transmission line here. At the input of transmission line, we said that the noise temperature is L minus 1 T naught, and L is the loss of transmission line, plus the mixer noise. It is considered to be an amplifier here, or treated as an amplifier here. So if M minus 1 T naught gives the noise temperature here. If we want the noise temperature at the input of a transmission line, we multiply by L, because the wave is coming in this direction. When we go in the opposite direction, the signal will increase. When we go in the same direction, the signal will decrease across the along the transmission line. Now the IF amplifier, okay, the noise temperature at its input is F IF minus 1 times T naught, and we multiply by the conversion loss of the mixer because we are going opposite direction, and we multiply by the loss of transmission line because we are going the opposite direction. Now we substitute the values. T antenna, we said it's 100 Kelvin. The loss is 10 dB. 10 dB is 10. 10 dB is also 10 as an absolute value, and the temperature is 290, the room temperature, Kelvin. The mixer noise figure is 10 also, and we said T naught is 290, and L is also equal to 10 dB the loss of transmission line 10 dB is equal to 10 also. If IF is 4 dB, 4 dB is equal to this 2.5. 4 dB, 4 is equal to 10 log FIF. So log FIF is 0.4, and 0.4 10 to the power x is 2.5. So it is, we put here 2.5, as you can see. It is 2.5 times T naught is 290 degrees Kelvin room temperature. LC, the conversion loss of the mixer, is 6 dB. Now let's convert also 6 dB is 0.6, 10 to the power 0.6. 0.6, 10 to the power 0.6 is 3.98, around 4. So we put here 4. And finally we have L, the loss of transmission line. It was 10 dB, 10 dB is equal to 10. Now we calculate this number. It is 100 plus 9 times 290, 9 times 290 plus, this is 9 times 10, 90 times 290, 90 times 290 plus, this is 1.5 times 4 is 6, 6 times 10 is 60, 60 times 290, and the answer is 46,210 Kelvin. This is the answer, same number exactly. Now the system noise power is, we add the K delta F. When we've found the TS, we calculated Pn by K delta F, and here by definition we multiply by K delta F. K is Boltzmann constant 1.38 10 to minus 23, and TS is given from here, system noise temperature, and the bandwidth we said it is 10 megahertz. 10 megahertz is 10 to 7. Now to calculate these values, 1.38, now 46 to 110 times 1.38 10 to minus 23, 1.3 times 10 to 7. The result is, as you can see here, if we multiply, this is 6.37 times 10 to minus 12. If we multiply by 10 to 12 to make sure that is okay, so it is 6.37 or 6.377 10 to minus 12 watts. This is the noise power. Now we want the input power, the noise power at the input of the antenna. This is the noise power at the input of the antenna. Now the signal to noise ratio is 1000. Okay. Now P received, we calculate P received from Fry's transmission formula. P received is taken from here. It is P input times the gain squared times lambda free space loss, which is lambda naught over 4 pi r all squared. This is P received. P received, here we write lambda naught is 5 centimeter, 5 10 to minus 2 meter, and 4 pi, the distance is 30 kilometer, 30 times 10 to 3 squared, and the gain was 40 dB. The gain was 40 dB. 40 dB is 10 to 4. We divide by 10 and 10 to the power 4 squared here, times P input. P input is unknown. If we calculate this, it will be here. This is 0.05 divided by 4 divided by pi divided by 3 times 10 to 4. 3 times 10 to 4 equal squared times 10 to 8 times exponent 10 to 8, and this answer is 1.76 10 to minus 6 times P input. This is P received. So we said P received 1.76 to minus 6 P input, and the signal to noise ratio is 1000. It is equal P received, which is 1.76 to minus 6 P input. This is P received. Signal is P received, and the noise is given by this equation here. We put here the noise. And we have one unknown in this equation, which is this is the unknown, P input. So P input is equal this times this over this. P input is equal to 6.377 10 to minus 12 times 1000 divided by this value, this coefficient 1.76 exponential to the power 10 to the power minus 6 exponent minus 6, and the answer is, as you can see, 3.62 10 to minus 3, 3.62 or 3.62 milliwatt. Same answer. Another example on radar. I will stop here now, and thank you for listening. If you have any question, any comment, please let me know. Thanks.